Let's consider a different kind of random process. Suppose we had a time series that was random and was equal to the weighted moving average of a white noise series. So the given data value is some given white noise value plus some parameter theta times the previous white noise value. This is called an MA1 process, or a first-order moving average process. Now, the autocovariance function is pretty easy to compute. We can compute it directly by substituting its defining equation. We can expand it into give these terms. And then we could notice that since we're dealing with white noise, the terms are non-zero only when the lag is 0 or plus or minus 1. When the lag is 0, we're left with this, sigma w squared once again being the white noise variance itself. At lag 1 or negative 1, we get this. And then we can use that to compute the autocorrelation function. It is 1 at lag 0, of course it always is. At lag 1, it is parameter divided by 1 plus parameters squared. At all other lags, the autocorrelation function is 0. Well, why stop at MA1? We can define an order Q moving average process. It will require Q different parameters, theta 1, theta 2, all the way up to theta Q. And a given value will be some white noise value plus a constant times the previous white noise value plus a different constant times the twice previous white noise value, all the way up to order Q. Once again, we can write this using the lag operator as an operator equation. And that allows us to define an operator, uppercase Greek letter theta, which is the MA operator. Now, you can often tell when a noise series is an MA1 process because there's a telltale sign of an MAQ process, namely that the autocorrelation at every lag greater than Q, and also negative lags less than negative Q, is equal to 0. So if you compute the autocorrelation function and it stops being non-zero suddenly at some particular lag, well, we know not only that it's an MA process, we can tell what the order of the MA process is. Now, you might wonder, is there a telltale sign of an AR process, ARP? Well, there is. Let's suppose that X is some AR1 process. And as we've seen, it can be written this way. Let's regress data values on previous data values without an intercept, because we're talking about noise processes that are zero mean noise processes. We will approximate our autoregression parameter by taking the slope of that regression, and then we can compute residuals, which will be approximately equal to our white noise process. Well, that's pretty interesting. We could also turn things around to say that the 2 times previous value minus the inverse coefficient times the previous value has this form if we work it out. So if we regress the 2 times previous values on the 1 times previous values, the residuals will approximate a multiple of the same white noise process, but at a different lag. Now here's what we do that's really very interesting. We're going to first take our data series and use it to define a new series. We're going to define it as residuals from regressing data values on their previous values. And we're going to define the other series as residuals from regressing twice previous values on the previous values. Notice they're both being regressed on the same fundamental quantity. Now, the first one is an approximation of the white noise process. The second one is an approximation of negative phi inverse times the white noise process at a different lag. Since they are at different lags, they're different white noise values and they're uncorrelated. So we could use their simple correlation to define the lag2 partial autocorrelation function. It's usually written as phi sub 2, kind of a clumsy notation if you ask me, but it's pretty standard, so we might as well get used to it. And it's the correlation between the residuals from regressing me on the previous value against residuals from regressing twice previous on the previous value. In both cases, regressing on the same fundamental variable. Well, that is the partial autocorrelation at lag 2. We could do the same thing at different lags. We could define a series which was the residuals from regressing a data value on the 2 previous values, and another one which is the residuals from regressing the thrice previous value on the 2 previous values. Notice both these regressions are using the same source variables. The first is an approximation of the white noise process. The second is an approximation of phi squared times the white noise process at a different lag. Since there are different lags, there are different white noise values, and they're uncorrelated. We can use their sample correlation to define the lag 3 partial autocorrelation function. And we can continue that process indefinitely to define as many lagged partial autocorrelation function values as we want. And we can also define the lag 1 partial autocorrelation function as simply equal to the lag 1 autocorrelation function. When we use this definition of the PACF, the partial autocorrelation function, it becomes a telltale sign of an ARP process, because it is 0 for all lags which are greater than the order of the ARP process. I'd like to show you some examples. Here's some data I generated, which is an MA1 process. If I compute the autocorrelation function of this MA1 process, notice that it is strongly non-zero at lag 0 and lag 1, but beyond lag 1, it's pretty much 0. It doesn't come out exactly equal to 0 because this is actual observed data, so it has random fluctuations. So this is just an estimate of the autocorrelation function, but it certainly gives the visual impression of dropping to 0, so that the biggest one is lag 1, telltale sign of an MA1 process. I also generated quite a few values, a lot of them, of an MA11 process. Here we can see that the autocorrelation function drops rather steadily. It is still non-zero, although it's small at lag 11, but beyond lag 11 it is 0, effectively so, which is again the telltale sign of an MA11 process. Now here is some autocorrelated noise. It's an AR1 process. I gave it a rather large autoregression coefficient, so it would have a fair amount of persistence. And you can see it really doesn't look like white noise because it's not white noise, it's autocorrelated. If I compute the autocorrelation function, we can see that it declines steadily as we expect it to, but it doesn't drop to 0 and then stick to 0. Now it gets as so low that we can't really tell it's different from 0, but it's not a suddenly stop thing. It's much more closely following an exponential decline, which is what we expect from an AR1 process. If I compute the partial autocorrelation function, it's different. At lag 1, it is not 0. At lags beyond 1, it is 0. It's still observed data from an actual process, so it's not exactly equal to 0 because we only have an approximation of the partial autocorrelation function. But the visual impression happens to be the correct one, that there is non-zero PACF at lag 1, but 0 PACF beyond that, which is the telltale sign of an AR1 process. I can also generate an AR2 process, and if I compute its autocorrelation function, once again we have a decline rather steadily of the ACF, but it doesn't give that visual impression of suddenly stopping. It gives the visual impression of declining steadily and approaching 0. If I compute the partial autocorrelation function, I see that I have 2 values that have non-zero values at lags 1 and lag 2, but beyond lag 2 it sure looks like it just suddenly stopped being non-zero at all, and that is indeed the telltale sign of an AR2 process. So, the autocorrelation function and partial autocorrelation function are good diagnostics for noise series. For an MA moving average process, the ACF will be 0 at lags above the order. For an AR autoregressive process, the PACF will be 0 at lags above the AR order.